Now, this is one of the most conceptual topics that we will study in chemistry. It has to do with the mass defect binding energies and how are those related to the relative abundance of the materials, of the elements. Okay, so note that we are talking about the abundance of elements here and not abundance of the compounds. See, the abundance of a particular compound, for example, which particular oxide of copper is most commonly found. Okay, so that kind of question, the compound, when we talk about element abundance of compound, that has to do with the chemical stability of that particular compound. So that has more to do with the electronic structure. Here we are talking about the abundance of element itself. So when we say like iron is one of the most abundant elements, silicon, carbon, those are some of the most abundant elements that we find around us. And why are those elements preferred to other elements, for example thorium, uranium, right? So that is the question that we are going to answer today. And of course the answer to such questions would lie not in their electronic configuration but in their configuration of their nucleus. Okay, so as soon as we talk about nucleus, there are two forces which should immediately come to your mind. Those are the strong forces and the weak forces. Okay, so sometimes it is not very correct to call them forces, so we would call them interactions. Okay, so strong interactions and weak interactions. So those are the things that should immediately come to mind because we are talking about nucleus here. So inside the nucleus you will find both protons as well as neutrons. We know that. Now, how come the protons, even though they are both negative, even though two protons would be negatively charged, the protons are negatively charged, how come two protons they stay together even when they have the same charge, right? There should be electrostatic repulsion between them. That's what we would expect. But even with that repulsion, there is something which is known as a strong force, which is stronger than that repulsion, and that is what keeps the protons together. Now, that strong force is actually orders of magnitude stronger inside the nucleus, right? At that small scale, very small scale, very compressed scale, this strong force is orders of magnitude stronger than the electromagnetic force. Okay, and that is why these the protons, when they come together, they stay together, and we would need energy to actually break them apart. Okay, so that is the first thing that we have to understand, that we would need energy to break them apart, which means that due to the strong force, if the protons and neutrons they come together, then they would likely stay together and they would lose energy while coming together. So this neutron and this proton, when they come together inside the nucleus, they lose energy. So energy is emitted out. And the interaction of the strong force is such that when these nucleons inside the nucleus, right? So neutrons and protons are together known as nucleons. So these nucleons inside the nucleus, when they come together, some of their mass is actually shared. Well, that is what the strong interaction means, that some of their mass itself is shared, which means that the net mass, their net mass actually decreases. So when these protons and the neutrons, when they come together, their net mass inside the nucleus, their net mass decreases, and that is what is shown here. So one of the most before we delve into this, but this is essentially what it is showing, that there are two protons and two neutrons inside the helium. We know that, and these come together, they are coming together, all of these, and they are going inside the nucleus. When they move inside the nucleus, when they come together inside the nucleus, the net mass of these protons and neutrons inside the nucleus actually decreases. So there is a decrease in mass, and this decrease in mass is known as mass defect. So mass defect is the decrease in mass of the nucleons when they come together inside the nucleus due to the strong force. So the strong interaction is such an interaction which actually reduces, which actually enables the, you can think about it, sharing of the mass between the nucleons, and that net reduction in the mass is actually released as energy. Okay, so there is a net reduction in the mass, and this is the energy which would actually be released, the equivalent of this energy. Okay, so how much mass is reduced? 0.03 AMU of mass is actually reduced when we go from the individual protons and neutrons, individual nucleons, to the nucleons inside the helium nucleus. Now, even before we go further, let us just understand what this AMU is. So this AMU is the atomic mass unit. It is a unit of mass. Similar, you can think about it in terms of kilograms. Similar to the kilogram, this is the unit of mass. And the unit of mass has been defined in such a way that it is 12 AMU is equal to mass of a C12 is equal to the mass of a C12 atom. Okay, so that is the definition. So 12 AMU is equal to mass of a C12 atom, and that is the definition of an AMU. So we have talked about this one, we have talked about the mass defect, and we have talked about the energy which is released when these nucleons come together due to the mass defect. And this energy which is released when the nucleons they come together is known as binding energy of the nucleons. So again, these are separated nucleons. These are the nucleons which are inside the nucleus. I would need to supply the binding energy to the nucleus, a large amount of energy to the nucleus, in order to separate the nucleons, individual nucleons. And that is what goes on, right? When we want to break the nucleus into its constituents, protons and neutrons, what do? We have to bombard it with lot of energy. That is what is done in LHC, Large Hadron Collider. What happens there? Their atom is smashing. There are two atoms which are smashed together. And why are we smashing them together? Because we want to break this nucleus into its constituent nucleons, and perhaps even further. I want to see what is even beyond, even inside these protons and neutrons. I want to see what is inside them. Okay, so we have to supply a large amount of energy to actually break the nucleons inside the nucleus into individual protons and neutrons. Okay, and that energy is known as binding energy. Conversely, if these separated nucleons they come together to inside the nucleus, then I get from this binding energy. Okay, and this is essentially the principle of the nuclear reactors, the nuclear fusion and fission. This is essentially the principle of that. Now we have discussed this binding energy, and what would be the value of binding energy is very important thing. Okay, so the binding energy. Okay, so there is a decrease in mass. Okay, this should not be smaller mass. This should be larger mass. Okay, so this is larger. Separated nucleons have larger mass, and there is a delta M. There is a mass defect, and this is known as mass defect. And this mass defect, due to this, we have a delta E. This is known as binding energy. So we'll put a suffix here B. And that binding energy is actually equal to the mass defect, how much mass has been decreased from individual separated nucleons to nucleus, how much is the difference in mass, multiplied by c square. Okay, and that is the Einstein, that comes from the Einstein's famous theory of relativity. So the amount of energy released is equal to the change in mass multiplied by c squared. So even a very small change in mass, for example, in the case of helium we saw it will be equal to 0.03 AMU only. There is a very small change in mass, but because it is multiplied by c square, okay, the square of the speed of light, 3 into 10 raised to power 8 meter per second, that is very large quantity, and we are squaring it. Therefore, because of this large factor here, even a small delta M would lead to a very large amount of binding energy. Okay, so that is the formula for binding energy in terms of mass defect, and this formula is of course very important. This formula is very important, and in the next class we will discuss a numerical based on this formula. So definitely subscribe to this channel. Now, in the beginning we talked about the binding energy and the relative abundance of elements, and this is a graph which shows the binding energy per nucleon. The more the binding energy per nucleon, the more stable the nucleon is inside that particular nucleus. Now here you will see that the most common elements such as iron, oxygen, carbon, nitrogen, these elements appear at relatively top of this graph, which means that these particular elements, their nucleons have relatively large binding energy per nucleon, which means they are relatively more stable in these particular elements. The nucleons are more stable, and that is why these elements are more abundant than the other elements such as uranium and thorium, which have relatively less amount of binding energy per nucleon, which means that the energy of the nucleons is not that much less inside these particular elements like uranium and thorium. Okay, so if you compare this with the graph that we saw in the very beginning, you will see large amount of correlation. Okay, and ultimately this is what we need to understand when we are looking at the relative abundance of elements. Another thing to note here is that these elements like helium, carbon, they will tend to fuse together to go to iron, and other elements like uranium and thorium, they would tend to fission. They will undergo nuclear fission and try to come to the more stable element configuration. Okay, a nucleus which has more stability. Okay, so hopefully things are very clear. In the next class we will be solving a numerical on binding energy, again very important. Okay, thank you very much.